Okay, very good morning again. So today we will further discuss our discussion on this statistical analysis from our previous class on Sunday, right? So if you still remember, we have talked about hypothesis, making our hypothesis, constructing our hypothesis. Okay, so I actually got a request, from some of you. To talk a little bit in detail on this hypothesis writing. All right, so here you are. So remember, when we are conducting our statistical test, okay, we always set up two contradicting hypotheses, so known as H null or H naught and hypothesis, alternative hypothesis. Okay, so that we can disapprove one or accepting the other. So always draw up two different opposite hypotheses that are actually related. All right. So to construct hypothesis, how we construct hypothesis is we take the research question that we want to answer. Okay. So we make a negative statement for H null and a positive statement for HA. Okay, alternative hypothesis. So the example of H null that we can write is relationship does not exist, okay, or difference does not exist between group. Okay, so when we say does not, so it means A is equal to B lah. So or before is equal to after, sample A is equal to sample B. So because we are saying they do not exist, okay, do not. When we say a not, okay, so it means equal lah. And for HA is supposed to be opposite of H naught. Okay, so for HA will be positive. So relationship does exist. Differences does exist between group. Okay, so when we say this, usually what it means is A is not equal to B. So sample A is not equal to sample B because they have differences. Before and after, they are different because A and B are different. The relationship or the differences exist. Okay, or maybe we say the monsoon impact on marine productivity does exist. So okay, so what it means is the marine productivity in the monsoon, during the monsoon, or after the monsoon show difference, right? So when our H naught will be differences. So it means if in the monsoon, during the monsoon, after the monsoon, right? The productivity is the same. Okay, so you can see the differences when we make H naught and HA. Okay, so a tip, if you already have a hypothesis, you want to write a research question, you just reverse the process. Okay, easy. So to make things easy, so I find this like an infographic from this .co or something. Yeah. So example of null hypothesis. Yeah. So you can see cats show no preference for food based on shape. So you see null hypothesis have a negative null. Okay, so it means the cat equally like the food of different shape. Okay, so equally like. So no preference. And the second example, plant growth is not affected by light color. Okay, so when you see not, it means null hypothesis. Okay, and basically it means the growth is the same regardless of color. All right, and the third example is age has no effect on musical ability. So it means the musical ability is the same for different ages. All right, so when we have something equal, it's not and null hypothesis lah. So equal, it means no effect, no negative thing. All right, so to put it in words, so you can see from here. Okay, so the question you can ask, are teens better at math than adults? Yeah, so this is the question we want to ask. Okay, the research question we want to ask. So remember, we take the question and we make it negative for null hypothesis. So it means, after we do that, it will become age has no effect on mathematical ability, right? So you see, it become negative now. So this statement converted into negative statement. Okay, so when we say no effect, so it's still equal, adult equal to teens. Okay, if you still remember from the class previously, so when null hypothesis, you usually have the equal sign. Okay, equal, less or equal, greater or equal. Okay, so anything equal, null hypothesis. Okay, and null hypothesis, when you write in words, it will be in a negative form. All right. So the H, if we say null hypothesis is like this, right? H has no effect on mathematical ability. So when we try to write into HA or hypothesis, alternative hypothesis, it will become positive. So it will become H has effect on mathematical ability. All right. So the next example, does taking aspirin every day reduce the chance of having a heart attack? So this is a question we want to answer. So remember, H now is it will change the statement to become negative. So taking aspirin daily does not affect heart attack risk. Okay, so when we write this, yeah, so it means you take it or not, the risk is the same, equal. Yeah, so I hope you can see the pattern here, because okay, let's see another example. Okay, like this one, cats, right? Yeah, I know a lot of people like cats, so let's talk about cats. Do cats care about the color of their food? Yeah, so this is the answer you want to ask. Do they care about their food color? So when you write H now, you become cat express no food preference based on color. So this means the cat like the food equally regardless of the color. Okay, so I hope you can see a pattern here. Null hypothesis, you change the statement to become negative. All right, so when you change it to negative, it means equal, right? Equal. So it's the same. Okay, so no difference, no preference, no effect. So the effect is the same, right? So when you write HA, when you want to write HA, so you just invert the H naught, okay? So when you no effect, become has effect. No preference become has preference. All right, so I mean, I asked the quiz there, but I already answered it just now. So the quick question now, does the occurrence of monsoon impact the marine productivity in the coastal water of Peninsular Malaysia? So what's supposed to be the HA and H naught? So, I mean, I already told you just now. So H naught will be no impact. HA will be has impact. All right, easy enough? Yeah, I might ask you a lot in this. I mean, I might ask you this a lot in exam later to make sure you really understand H now and HA, because this is the most important part when we conduct research. Okay. So now you already know how to write your H now and HA. So which one we want to disapprove, right? Sorry, we want to disprove or we want to reject. Okay, so we want to reject the negative. We want to reject H now. So why? Why so? Okay, the reason is because we cannot prove something that is negative or something does not exist. Okay, we cannot prove that there is no effect. Okay, it's difficult. All right, so you can see a lack of evidence of something does not exist. It does not mean we prove it does not exist. Okay, I mean, you can catch it. So if we try to prove something does not exist, we don't have the evidence, but it does not mean it is not there. It might be there, right? But your study fails to discover it, right? So it's just like, I mean, example, people say, oh, a certain species of animal already extinct, you're no longer there. Then suddenly, a few years later, they discover, hey, this species still available, right? So it's very, very difficult to prove something does not exist. All right. Okay. So because it might happen because when we get something like no longer exists, like the animal already extinct, no longer exists. Yeah. It might be just be our study failed to discover it. Okay. Maybe our study failed to cover all ground of our field or something. Yeah. So it might be the weakness from our study that resulted, we think that something does not exist. Okay? So always remember this. lack of something, lack of evidence of something does not exist, it does not mean it is really not existing. All right. So what happens if we fail to reject H0? Okay. What if we fail to reject H0, meaning we accept that something does not exist? Okay, in our test. All right. So there are two possibility. One, it is really does not exist, or our test failed to detect it, like I told you just now. All right. So our test maybe failed to detect it. Okay. So we don't want to like take assumption our test is perfect. Okay. So we can say, oh, this effect is really not existing. Okay. But so we have to take into account our test have the possibility fail to detect the effect. So even though we see something is not there, maybe it's there, right? So just like people say, do you believe in ghosts? Is the ghost like exist? So you just answer, I am a scientist, okay? Because we cannot prove ghost is not there, but does it mean it's not there? Maybe it's the way the technology we have now, we cannot detect, right? Okay, so just remember, so as a scientist, when we say we cannot, I mean, when something does not exist, we found something does not exist, it might mean our test failed to pick up its existence. Okay, provided the thing that you claim makes sense. All right. So remember, we cannot say we proven H0, we simply fail to reject H0. All right. So we cannot say we fail to prove it does not exist. You just say we fail to reject that it is not existing. All right. So be careful of your word, okay? Because it is I mean very important when we try to claim something. So especially as you are as a scientist, if you claim something, most likely people will believe. All right. So we don't want to spread, I mean, misleading information to general public. So always remember this. Okay. All right, let's go to this case study. All right, so we talk a lot of this H0, HA. So example, I think you learn from example is the easiest. Okay, so the same question we want to answer. Does cat prefer food with certain colors? Right, so it will be easier. Okay, so the question is like that, right? So we write your H0 is it does not have preference. HA is it has preference, right? So it will be easier to test if the cat have preference over food than to prove that cat does not have color preference over food. So how different are these, right? So we want to test if the cat has preference over food, and you want to test the cat does not have preference over food, color preference over food. These are, I mean, it sound when you think it like it sound macam similar, it's the same thing. Actually, it's very different. All right. So when you want to test if the cat have preference over any food, so we just give the cat any color. Okay, regardless of the situation. Regardless of the situation, regardless of the species of the cat, as long as the cat have a preference, show that it prefer one color, okay, we can already reject H0, regardless of any situation. Okay? If not, if you want to prove cat does not have preference, color preference over food, a lot of things you have to consider. First, the cat breeds, the species, the color of the food. I mean, sorry, how to say? Sorry, the type of the food. Yeah. This is correct. So you have to consider the cat breeds, okay, or the species. Okay, maybe different cats. Some cats have preference, some cats don't have preference. So you have to be very careful on the selection of the cat type or your how to say your sample. So you have to be very careful in selecting that. And you have to make sure all the food color available to the cat so that they can choose, right? Just to show that cat really does not have preference over food. So you see, the workload you can compare, right? You want to prove it has preference, and you want to prove it has no preference. When you want to say it has no preference, you have to consider every single variable. Cat breeds, food color, and also a food type. I forgot to write in the type of the food, right? If you give the cat eat vegetables with different color, so the cat don't like veggie, it will not eat anything. So you just say, oh, cat don't like they don't have preference over color, food color. It can be misleading. Maybe when you have meat, right, you give the cat meat, you give the cat the cat biscuits, right? So when you have a certain color, it will prefer a certain color, right? So we cannot remove the possibility of other variables might might have an impact on our outcome. All right. So let's say if we think we already consider all these variables, so there might be still other possibility which we did not think of. Okay, meaning our test maybe failed to pick up other variables that might affect the cat does not have preference over food. Okay, for example, the food not suitable, like I told you, you give the cat vegetables. Yeah, cat don't like to eat vegetables. So it will not pick any color, right? Or maybe the cat, it was stressed out during the experiment, so it eat anything. It's so stressed out, or it's stressed out, it don't want to eat anything. Okay, so there are other variables that might impact our hypothesis. So that's why you can see it will always be easier to prove something that exists compared to prove something that does not exist. Okay, so I hope you are clear on this. If you are not, read this example a few times. Okay, so after you write your hypothesis, you're done the first step. So the second step is you have to decide significant level, alpha. Okay, I believe you follow a lot of your statistical class. You heard a lot of this alpha, significant level, alpha. So what is actually significant? What is actually alpha? All right. So if you still remember from the class previously, so alpha is the probability we make type 1 error, meaning we reject H0 while it is true. Okay. So you reject H0 while it is true. So you can imagine how H0, how it's true. For example, Dr. Jun's weight is affected by Dr. Jenny, how much Dr. Jenny eat. Right? Obviously, it's not true, right? So my weight is because how much I eat, not because of how much Dr. Jenny eat. Okay, so we want to know the probability we make type 1 error. So that one is alpha. Okay, so remember, alpha is the standard we set. We give the standard. Okay, so like how extreme our test can be so that we can confidently say that H0 does not exist. Okay, so remember, if we set the alpha to be very small, so our test must be very stringent. Okay, so alpha, it has a maximum value of 1. Okay, so if we say alpha equal to 0.05, it means there is 5% of the 5% chance we made type 1 error. Or in other words, let's say we set alpha to be 0.05, it means we allow ourselves to make type 1 error at 5% of the chance. Okay, or 5% of the probability, we allow ourselves to make type 1 error. Okay, so you have to remember, while alpha is often set at 0.05 or 5%, this is not the absolute standard. Okay, not we have always, all the tests we have to set 0.05. Okay, because I encounter a lot of students, they always tell me they have to set alpha to 0.05. Okay, in fact, it depends on your study. All right, if your study allow larger margin of error, you can even set the alpha to be 0.1 or even 0.4. Okay, meaning 40% of the chance what you get maybe is wrong. It depends on your test. All right. So example, let's say you are a pharmaceutical person, you want to make vaccine, or you want to you make some medicine, right? So you want to know this medicine will be harmful to human or not. All right. So obviously, when you are working with medicine, you are how to say, you are actually have a say in human life, meaning what you do will impact human life. So you want to reduce the error. Okay, you don't want a lot of people to have a negative error, negative side effect from your medicine, right? From your medicine. So you will want your test to be, you want your alpha value to be as small as you can, right? As small as it can, right? We don't want like, okay, there are 40% of the chance you eat the medicine, it will die, right? We don't want something like that to happen, right? So maybe 1% or even less than 1% is okay. All right. So remember, it depends on our test. Alpha value is not set in stone. 0.05 is just commonly what people do because they think, okay, 5% of the time you do something wrong, probably it's still fine. Okay, but it always depends on our test. Okay, on our research question, on what we want to do. Okay, so let's say if we are doing something, is allow like larger margin error, we can set the alpha to be larger, 0.1, meaning 10% of the chance you make a mistake, make a type 1 error, or even larger. Okay, but if your test have to be very accurate, okay, you set your alpha to be small, like 0.01. Okay, meaning only 1% of the chance you can make error or even smaller. Okay, so always remember, alpha is set by us, the investigator, not set by anyone. Okay, we decide it ourselves. Even though you see 0.05, if you put 0.05, it means you accept 5% of error. Okay, so it is set by us to represent how stringent our test should be, or the chance we allow ourselves to make type 1 error. Okay, rejecting H0, but it is actually true. All right, so you have to always remember, alpha is decided by us, not by anyone, not by your statistical test, okay, but by ourselves. So, but you have to always remember, okay, if your test is too stringent, meaning alpha level too low, you increase the chance you make type 2 error. Okay, so type 2 error is opposite. So you accept the hypothesis, well, it is wrong. So this is something we want to avoid. Okay, so it is still okay, you reject something true, but accepting something wrong is usually unforgivable. Okay, so you have to always remember, right? If your test is too stringent, you increase the chance you make type 2 error. Okay, accepting something that is wrong. Okay, so I hope you are, after this, you are clear what is actually alpha. Okay, when you see alpha is 0.05, you know, okay, this researcher is set, it allowed the error to be 5%. So when come to yourself, when you want to work with your PITA project, right? So you want to do a statistical test, you have to think, right? If you do this, how many is something of this allowed to have a larger margin error, or you have to be very accurate. Okay, usually larger margin error, you can use it, okay, when you want to test something, let's say it has a lot of variation, okay, it might have a lot of uncertainties, okay, something that we cannot measure. So probably it's okay to have a larger margin of error, but remember, it's not the rule of thumb. It not mean, oh, something not you are uncertain, you can set it a larger margin error. It's not always like that. You always back to your research question and you have to think. Okay, so remember, alpha, you set it yourself. All right, so after we set our alpha, we have we set our hypothesis, we set our alpha. Now we are going to test our hypothesis. So we are going to conduct statistical tests. So before conducting statistical tests, you will come across something known as p-value. Okay, so what is actually p-value? So p-value is the probability value associated with your statistical test, or the likelihood of the observed statistic that you calculated occur by chance. Okay, how likely the something you calculate, let's say the mean you calculate, is just happen by random. Okay, how likely it will be like that, right? So this is p-value. Okay, so when you conduct a statistical test, it will give you a p-value. So you get this, you take this p-value and you compare with the alpha you set. Okay, so we take the p-value and compare to the alpha value that we set. So by doing this, we are trying to determine if the observed data or the statistics are statistically significant from our H0. Okay, so remember, statistical test is we test H0, right? So when we compare the p-value to the alpha level that we set, so we are actually trying to determine if the observed data are any different from H0, from what we claim. All right. Sorry, another one. Yeah. So if the p-value we get from our test is less or equal to alpha, So we can reject H naught and we say our test result is statistical significant. Okay, because something happened by chance is lower than the error we allow ourselves to make. Okay, so we accept it. We can reject the H naught and say that our test is significant. Okay, so this is very common, right? But if the p-value is larger than alpha, we will fail to reject our H naught. Okay, because it means the probability of our statistical test is larger than our, the probability to get the result from our test is by chance or randomly we got it. The probability to get it as a random is higher than the error we allow. Right? So we say our test is statistically significant, non-significant, or something like that. Okay? So remember, p-value smaller than alpha or equal to alpha, we reject H naught, saying our statistical test is significant. If larger than alpha, we fail to reject H naught, saying our result is insignificant, statistical insignificant, or statistical non-significant. All right? So remember this. But they are gray area. Okay, that said, they are gray area. For example, let's see, quiz. Right? So we decided that the alpha for our statistical test should be 0.05. Okay, we decide that our test can tolerate 5% of error. Okay, so we do our test and we get our p-value 0.06. So is our test result statistically significant? So that's the thing I want to ask. So remember, alpha is 0.05, p-value is 0.06. So p-value is larger than alpha. Okay, so you will tend to reject, or you will tend to say you will tend to accept H naught, okay, and say our result is insignificant. Right? But is it really that way? Because you see 0.05 and 0.06, it has a very small difference. Right? So let's say if you set your test to have an alpha 0.05, of course you will say your result is not statistically significant. Right? But what if you increase your alpha? You increase your alpha to 0.6, 0.06, 0.07, 0.08. Right? So P will become smaller than your alpha. It will become significant again. All right. So remember, there's always a gray area when you use P and alpha. Okay. It will not always, it's not always fixed. Okay. You can decide it later. Okay. For me, I will not set alpha first. Okay. I will calculate the p-value first and I see. Okay. When I see the p-value and I decide the p-value I get is like this. Okay. So can my assessment of something tolerate this amount of error? Okay, let's say if I get my p-value 0.0555, 0.055, yeah? So I see 0.055, I think, yeah, my work or my statistical test, it can tolerate error, maybe 10% doing something, 10% wrong is still okay. So I will accept it. I will say my result is significant at, see, you set the area, alpha, okay, 0.1, let's say. Okay, so how different scientists look on alpha and p-value, it might be different. Okay, so other scientists might work differently. They will prefer to follow the usual standard alpha. You set your alpha, you decide your test. You set alpha, you do your statistical test, you take the p, and you decide you should reject H naught or not. Okay, but my approach is I look at the result first. Okay, I look at the result and I decide I want to reject it or not. Because remember, alpha is something we decide. Okay, it's not set in stone. It's not always 0.05. You can even set it if you like to be very fancy, 0.07. Right? You can even say it like that. Okay, so have to always remember alpha is something you can set. So P is the probability, the result you get by chance. Okay, depending on actually how large you can tolerate the error. Okay, you can adjust a little bit your alpha. Okay. Okay. And you have to always remember, when the p-value is very low, right? It does not necessarily means alpha is false. Okay, it is just probably it is false. Okay, p-value. P-value means probability, the probability. All right. So if you get the probability 0.01, it just means there is 1% of the chance H0 will be false. It's actually false. All right. It's not. It does not mean H0 is really not true. Okay. So remember, when you talk about statistics, we talk a lot about probability. Okay. And there are three. Obviously I already mentioned this. So p value of a hypothesis test, it depends on the nature of your test. Yeah, like I told you just now. Yeah, the test maybe it allow you have, let's say you get a p value 0.06, but your test actually allow a 0.1 1%, 10% chance of error. So you can actually accept it. So you remember p value, it depends on the nature of the test. Okay, and the calculation of p also depending on what hypothesis test to use. Okay, so there are actually three ways when we do a hypothesis test. Yeah, there are three ways that we usually test this p-value. So remember, there's three ways. One is a left tail, right tail, and two tail. Yeah, so let's look at the next slide. Yeah, let's look at this. Okay, so left tail test, you can see like this. Okay, so p-value is located at the left. Okay, so this is a left tail, example of a left tail test, right? So when you run to write a left tail test, I should put it like this. Okay, the left tail test, right tail test, two tail test, it depends on your hypothesis. Okay, it depends on your HA. Do I write it there? Yeah, it depends on our HA. So this type of test, it depends on the region of the sampling distribution that favors the rejection of H0, meaning the region of our HA, right? Yeah, I should say here. So it's on our HA, the region that we can accept our HA, like this. So let's say you have a let's say look at left tail test first, one by one. We go slowly, no rushing. So H0, our H0, all right? So our mean is larger or equal than K. So our HA will be less than K. So when you have something less than, you go to the left. You look at the left, like this. Okay? So very easy. If you don't remember, you just look at this symbol. Okay? If your hypothesis HA is going to the left, you are doing a left tail test. All right? So if your hypothesis A or your alternative hypothesis is going to the right, P meaning mean more than K, more than, something more than, you go to right tail test. Okay? So if your hypothesis is not equal, okay, so it will become two tail test, like this. Okay, the blue one. So why this is important? Okay, because the difference of this test, it will decide the value of your P. Okay, so you already decide it's 0.05. Okay, so when you have the left tail test or right tail test, the P you are going to assess will be 0.05. All right, but if you have a two tail test, you have to divide the P by 2. Okay, so meaning when you set your P value to be 0.05, it will become 0.025. Why this is important? Because it will help us to decide something known as critical value. Okay, the limit that we should start to, or the limit, or the maximum limit we can reject our H0, or you can think it like the minimum limit where we will start to accept our HA, depending on how you see. So you can see that this line, they draw this line, right? So this the value here is what we call critical value lah. Okay, so we will talk about it. What is critical value later lah, when we look into like Z test or something. Okay, so remember, this is important for us to decide the critical value, or the, I would say, rejection range or something like that. Okay. So remember, p value depending on the test you use, right? Left tail, right tail, two tail, the value change lah. So left tail, right tail, it will be the same. If you set, okay, it will be the same. But for the two tail test, you have to divide by 2. Okay. So let's look at various ways we test hypothesis. Okay. So remember this section of the lecture is not going to train you to become like, oh, you really are expert in this test. It will more like introduce you to like what are the tests you can use. Okay. So let's say if you favor Z test, you want to learn more about this Z test, you really have to read up a statistical book. Okay. So in Oceania, I share you a book, okay, on elementary statistics. So it will give you a various example of these tests. Okay, so let's say if you really need to use Z test, refer the book. All right. So without further ado, let's look at what is actually Z test when we are going to use it. All right. So you have when we want to test mean, you want to test the mean. Okay, a mean of let's say 1 sample, 2 sample, or the difference between the sample mean, right? So you use Z test. You can use Z test when, yeah, you want to test the mean and the standard deviation. You know the standard deviation, okay? And you have to make sure your sample is random and the population is normally distributed. Okay, I hope you still remember what is normally distributed. And the sample size must be larger than 30, larger or equal to 30. So this is the thing, the criteria you have to I would say you have to achieve. Okay, the criteria you have to meet, okay, in order for you to be able to use Z test. All right, so Z score is equal to sample mean minus hypothesis mean divided by standard area. All right, so you can see the formula here lah. Okay, so remember standard error is actually the standard deviation. A standard deviation for your statistics is the mean, median. All right. So how deviate it is, because your sample mean standard deviation, I say. How deviate it is your sample mean from the population mean. All right, this is a standard error lah. So just go through. All right, so the SOP when you want to do Z test. So first you verify that the standard deviation, you know the standard deviation. Okay, the sample is random. It is normally distributed, or your sample size is larger than 30, because as your sample size becomes very large, you approximate to normally distributed. Okay, so this is the SOP when you want to do this statistical test. So after you decide, okay, you achieve this criteria, okay, your data or your sample met this criteria. So you proceed to state your hypothesis. Okay, so what you want to test. Then you decide your alpha, okay, how much error you can tolerate in your test. And then you calculate the Z value, okay, based on the formula is here, Z value. Okay, then you find the area corresponding to the Z area, the P value. Okay, so you can see from the graph here. All right, so you have to find your Z. So is your Z fell in somewhere here or not? Okay, so let's say Z naught. Z naught is the critical value. Okay, the range you can start to reject your H naught. Okay, so this range is depend on your alpha actually. Okay, but when you look in this what is it called again? The table, okay, the Z score table. Yeah. So you want to find, let's say 0.05. Okay, so you look at all the table. So what is the critical value? What is the Z naught? Okay, so let's say and you see if your Z score is smaller or larger than the critical value for left tail test, so you can safely reject your H naught. Okay, let's say you decide the alpha to be 0.05. Okay, so you calculate you go and look up the critical value. Okay, so let's say if you are doing a right tail test, meaning more than, okay, so you find also the critical value. Okay, they have this table. I think in the past during our secondary school, so we have a book, right? We have a book. You write let's say Z test. So what is a critical value? If you want to set the significance of this database, it has a book. I don't know, maybe during my time it has a book. Maybe your time you already no longer use it, but it has a table to look on that. Okay, so you decide. Let's say okay, you want a 0.1 alpha value. So you go and look up this critical value. So if 0.1, let's say if 0.1, it means the area under the curve, 0.1. So what is the Z0 or Z0 or critical value? Okay, so you decide what it is. After you decide from the table what it is, you compare back with your the Z value you calculated. Okay, so if the Z value is larger than the critical value, you can reject the H0. Okay, and remember for two-tailed test, yeah, the P have to be divided, right? You have to divide by 2. So you also divide your alpha by 2. Okay, so let's say you want to set 0.1 as your alpha, right? So remember, for two-tailed test, you have to divide by 2. So you divide the 0.1 with 2 becomes 0.05. So you go and look up what is the critical value. Okay, so if your Z score is smaller than the negative of the right side, yeah, I mean the left side critical value smaller than the left side critical value, like this one. Here in this case it's negative lah. Okay, so you can reject H0. If larger than the H0, you also can reject the H0 because you are doing a two-tailed test. Okay, then you have to after that you see if the P value is larger than A or smaller than A, smaller or equal to A or larger than A. So you decide you want to accept or reject the H0. Okay, so this is just the standard procedure. Okay, you can see it's like you have to know your data, state your hypothesis, decide the alpha, conduct your test, right? Identify the P value. So decide if the P value is smaller than your alpha or equal to your alpha, then or is larger, then you decide you should accept or reject H0. So this is the flow of hypothesis tests. Okay. So the next one we commonly use is a Z test. Okay. So this is when we use t-test when we want to test again mean, right? We want to mean, but now we don't know the standard deviation. Okay, we don't know the standard deviation, but we want to test the mean. Okay, so the criteria is the sample is random, it has to be normally distributed, or sample size larger than 30. Okay, so in t-test, you have to take into account degree of freedom. Okay, so for t-test, the degree for freedom will always be n-1, the sample size minus 1. Okay, because we don't know the population standard deviation, right? So we have to use our sample standard deviation to approximate this sigma, this standard deviation. So if when we do this, we lose 1 degree of freedom. Okay, so remember when you want to test mean, but you don't know the standard deviation, you use t-test. All right. So same thing, the SOP very similar. So you can see, so same thing, verify if the S is known. If you don't know, yeah, and you have to make sure the sample size is random, it is normally distributed or more than 30. You state your hypothesis. Okay, the second step, you state your hypothesis. What you want to test? What you want to test by using this t-test. Okay, then decide your alpha, identify the degree of freedom, you calculate the t. Okay, you calculate the t, then of course you find the critical value, okay, or the rejection region based on the degree of freedom and of course the p value you want or the alpha value. Okay, again they have a table, t table, you can just check, so you can identify what is the critical value lah. So then you ask, is your t inside the rejection region? Yeah, if it is, then you can reject your H0. If it's not, then you have no choice but to accept your H0. So you can see, so the flow is like this. Okay, when you do statistical test, this is the flow. Okay, it will be the same for other tests as well. Okay, so you identify the criteria. First, you identify the criteria of your test. Does your data fit the criteria? This is the first thing. Next, you state your hypothesis. Then you decide the error that you can allow in your test. Okay. Then you decide, then you calculate the statistic. After you calculate the statistic, then you see, okay, should you or should you not accept or reject your H0? Okay, this is the standard procedure. Okay, I hope you can see this pattern. Okay, you see from the Z test and the T test, they are basically the same thing. All right. So the next commonly used test is a test for variance of standard deviation. We call it chi-square test. Okay, not chi, chi-square test. Okay, so this is when we want to test variance of standard deviation. Again, your sample have to be random. Yeah. So why you need to be random? So if you don't remember, please refer back the slide in the previous lecture. Why the sample have to be random? Okay. So the third criteria is your population has to be normally distributed. All right. Then again, you have to decide also the degree of freedom. All right. So this is basically the formula. All right. So chi-square, the value is equal to the n, sample size minus 1 is the degree of freedom, times the sample variance divided by the population variance. You get a chi-square. So by right, yeah, I also read the SOP. And by right, I should just let you, you already know the pattern. You already know the drill, right? Verify it meets the criteria, blah, 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 state the hypothesis, decide the A, alpha, okay, identify the degree of freedom, calculate chi-square, okay, find the critical value on the rejection region, right? Then you ask, the chi-square you calculate, is it in the rejection region or is it outside the rejection region? Okay, then based on this, should you accept or should you not accept the H0? Okay, so you can see the pattern now. Okay, so this is the flow that we want to conduct statistical test. Yeah, I think because the next one I will no longer write this SOP. I assume you already know. Okay, so the fourth test that usually people use is the comparison between two variances, two or more variances. Okay, this is called the F test. We use F distribution. Okay, so you don't really have to care a lot on this jargon, but it's always good to know what is actually F distribution. Okay, so you use when you want to assess the quality of variance. I left out words there. Okay, between two population. Okay, you want to assess the variance, and the sample have to be random and independent, and the population have to be normally distributed. Okay, so you can see this is F equal to variance of sample 1 divided by variance of sample 2. Okay, so F test is frequently known as used in ANOVA. Okay, so I will talk a little bit about this. I will say introduce, not talk. Introduce a little bit about this ANOVA because ANOVA is frequently used in I think biological other field, not that much in my field. Okay, so ANOVA they have two types. One is one-way ANOVA and this two-way ANOVA. Okay, so most likely you will use one-way ANOVA. So it can use to compare the means of 3 or more population. Okay, so two-way ANOVA, yeah, you can test up to 3 H0 in one go. All right, so ANOVA is very useful when you want to test a lot of sample. Okay, let's say you have 3, 4, or even 10 sample. Okay, usually you want to test something very quickly, so you will use ANOVA. Okay, so using, let's say, example, one-way ANOVA, it can quickly tell us whether at least one of the mean is different or not. Okay, it can tell us. So you test, let's say you test 3 things, okay, or 3 chocolate types. Let's say a chocolate made from different type of bean. Yeah, will anyone prefer a certain type or not? So you test the mean. By using ANOVA, you can quickly test these three things. Okay, so you can tell, oh, they actually have difference, right? They actually have difference. So this is what we want from ANOVA. Okay, but ANOVA, it has one downside. It cannot tell us among these 3 which one is different. We cannot know. Okay, so we have to do further analysis. So I always like to think ANOVA as like a filter. Okay, if you tell me, let's say I have a few samples, if you tell me, do I need to continue further doing analysis? Okay, let's say if you want to compare 3 mean, 3 different things, okay, or 3 different groups, if my ANOVA tell me they are just the same, okay, so then you can just bungkus and balik. Okay, no need to do further analysis. But let's say ANOVA tell you, hey, at least one of them are different, or at least one of them is different. So no choice. You have to do further analysis to find which one is actually different. Okay. So, and for two-way ANOVA, I'm not sure. For me, I think we will seldom use it in our case. I'm not sure. Okay, because I often need the most we use is this one-way ANOVA. Okay. So the prerequisite you want to use ANOVA is each sample must be randomly selected from a approximately normal population. Same thing. Okay, everything need to be normally distributed, and the sample must be independent of each other lah. Okay, and they have to have the same variance. And for two-way ANOVA, the sample size must be equal. Okay, so you decide should you use ANOVA or not. Okay, if you want to use ANOVA, why? Okay.
Dr. Chung hilang dah orang.
Tests the correlation and regression. Okay, this is very important, and all.
Sorry, you went sangkut. You went missing, Chung. Sangkut lagi.
You know, some people to study relationship between two variables.
You repeat a bit, cause you hang a bit, so you're missing for a while.
Which one for the correlation?
This one now you start again.
Okay. So let me start again this correlation part. Yeah. So and correlation and regression, or correlation. Let's start with correlation first. All right. So correlation is the I would say a very important test, very useful test that always misused by I would say some people who have I don't know, have a bad intention or something, or you have poor understanding of this correlation. So it's something that often really being misused lah. Okay, so let's look at what is actually correlation. So it's a study of relationship between two variables. Okay, you can see from this first figure. So there are various type of correlation. You can see like this. There are four. So you can see the data spread like this. So Y is a variable. Where we want to, let's say, test the relationship between X and Y. This is X and Y. Variable X, variable Y. All right. So you can see if you when you plot the relationship like this, when you plot the data, X and Y like this, you get a straight line like this going downward. It means X and Y have a negative linear correlation. So what does negative linear correlation mean? Yeah. So basically it means you can see from the graph. All right. So when X increase, Y decrease, right? Increase, Y decrease. When Y increase, X decrease. Okay, so this is linear, negative linear correlation. If positive linear correlation, basically means if X increase, Y will also increase. All right, this is positive linear correlation. And another type is there is no correlation. So when you plot the data, right, X and Y, so it will be scattered around. Yeah, this is no correlation. So another type of correlation is called non-linear correlation. Okay, non-linear correlation it can be like this one. So when you see this pattern, so basically what it means, so when X increase, Y will also increase, but when X reaches a certain point, Y will decrease. Okay, you can imagine like the spring. Okay, if you pull the spring get longer, right? No, spring probably is not a good analogy. Okay, I'm not sure how. What is the best example? Because I know a lot is from air quality. Like I say, People always say when you have a more temperature, you will have more ozone being produced on the surface. Yeah, but actually it's not true. Because when, of course, at first, when the temperature increased, the ozone also increased. But at a certain point, yeah, if you have more temperature, the ozone will decrease because it has a harder time to form. Yeah, so yeah, some example like this. And so this is non-linear correlation. Okay, it might be increasing together, then eventually one increase, it will decrease. Yeah, non-linear, not in a straight line. Okay, so like this. Then yeah, let's take note first. Look at this take note part first. Yeah, so correlation coefficient R, usually we call it R, is the measurement of relationship. It can span from -1 to 1. Okay, so when you have a negative, it means negative correlation. When you have a positive value, it means positive correlation. Okay, I'm not sure. Yeah, I don't have example of 1. So basically, when you have 1, yeah, it means it's just one straight line. Yeah, I have, sorry, yeah, here. Oh my God. So when you have a 1, correlation 1, it's just one straight line. Negative 1, also one straight line. Okay, so when you have, let's say, R equal to 0.81, so you can see the data almost one straight line, but there are some, I mean, some scattered around. Okay, this is like 0.81 when you get a 0.81 R value. Yeah, or even we go down lower, yeah, when we go down lower, you can see the straight line is still there, but more data point is being scattered around. Okay, so this is what R value tells you. All right, and I mean the same thing for the negative one. So when you have 1, so everyone is in the straight line. Okay, everyone follow the line. When you have a little bit deviation from 1, okay, decrease from 1, -1, so you can see the points started to scatter around. All right, so this tells us the strength of the relationship. Okay, so if the relationship is totally absolutely strong, so Y increase, I mean, sorry, X increase, Y will increase. Okay, Y increase this much, Y will always increase this much. Okay, but sometimes it may be not so much, right? Sometimes X increase like this, Y increase like this, or sometimes Y increase more or increase less. So you will have different value of R. All right. All right. You have to always remember, okay, when R value is high, it does not mean X cos Y. All right. Why? Yeah. So why is this case? Yeah, I told you just now, right? When the R value is high, the relationship between two variables is high, is strong, right? But when the R value is low, the relationship is weak. Why we say high R value does not mean X cos Y. Okay, the reason is sometimes when we calculate, let's say two data set or 2 time series or 2 sample of data, you might end up R value very high, but they are actually not related. Okay, example, the plate of rice Dr. Chung eat, and let's say a certain student A in data analysis eat. Again, you have this data, so we calculate how much plate of rice we eat every day. Okay, my number, then a student number. So we run an R test. Oh my God, we get a R high value, very high. So we will say, oh, the number of plate Dr. Chung eat, I mean the number of plate of rice Dr. Chung eat is related to student A, right? But in actual, there actually no relationship. It just so happen to be like that. Okay, so you can see correlation test can be easily manipulated. Sometimes when you put 2 time series, right? Yeah, or two sample, 2 data set or 2 variable, you run the R value, it gives you a high R value. Then you say, okay, these 2 must be related. But it might be not the case. It might not be the case. Okay, it might happen just by chance. Okay, so when using correlation, when you want to use correlation, you have to remember to ask, is there a direct cause and effect relationship between variable or not? Does the relation, is X really related to Y? Okay, is that really direct cause and effect or not? Okay, because you have to come up with hypothesis, right? So you cannot just simply come up with any hypothesis. You have to be making sense. You have to have a background knowledge of your study. Okay, so you have to ask yourself, X and Y, are they really related? Okay, then first, is there a reverse cause and effect relationship? Basically, this is the same. So does X cause Y or Y cause X? Does X causes Y? And another you have to ask, does Y causes X? So these two things are actually the same thing. So you have to ask this. Okay, are they actually related? Okay, so the next thing, is it possible the relationship between X and Y is caused by third variable? Okay, this is a very simple case, right? So you test the temperature. Okay, the temperature, let's say the temperature in let's say Kuala Terengganu coastal water. All right, then you take the strength of monsoon. Okay, you do correlation. Then you realize, hey, they have strong R value. So, okay, but you have to remember, aside from monsoon causing the change in temperature, and so maybe causing the change in temperature as well. So they are third variable that might affect our result. So you have to ask, is there any third variable that might resulted or change, affect the relationship? Okay, then of course the last one you have to ask, let's say X have a relationship with Y, is it just by chance and you get this R value? Is it just by chance you get a higher R value? So you have these few things you have to always ask yourself when you do this correlation test. Okay, is X and Y really related? Is there anything that might actually cause them to be related? Or is it possible the relationship just by chance? You get the R value, high R value by chance. Okay, this is a few things you have to think. Okay, so even though people present you, okay, I want to mention this. Let's say if somebody present to you some statistical test telling you, oh, this have a very strong correlation, because the R value is high. Okay, this is very common. You can find, let's say, in fake news also. They say, oh, this actually caused this actually caused this. Because they, and they show you this statistical test, R 0.9. So you have to take a step back and ask this question. Okay, is the thing present to you really have a cause and effect relationship or not? Or is there any third party that might cause this relationship? Is the relationship happen by chance? These are a few things you have to think. Okay, remember when you test hypothesis, it helps you to do critical thinking. Okay, so that you will not easily be misled by this fake information. Okay, so make sure you remember this, because correlation test is always being misused by party of interest. They want to do something, so they use the R test. Okay, sorry, the correlation test give you the R value. Okay, so you have to remember that. And when we want to test the significance of this R value, we usually use t-test. Okay, we usually use t-test. Okay, so I hope you are now clear with correlation, the potential downfall of correlation, and we want to do a significant test. What are the tests? Do t-test lah. Okay, so I'm not end yet. So when you have correlation, sorry, anything? Yeah. So when we talk about correlation, the next thing we cannot escape will be regression. Okay, regression is not actually a test, okay, but it's an extension of correlation. Okay, okay, let's go with the flow first. Okay, be patient. So after verifying the existence of linear trend, linear correlation between two variables, okay, so we want to identify the best fit line for our data. Okay, let's say we have a data like this. So what is the best fit line that actually tell us about this relationship of the data? Okay, so this line usually called a regression line, best fit line. Okay, where the sum of square or the deviation, if you still remember sum of square from last week class, is the minimum. Okay, so one straight line that fit our data. They can describe our data because we want to generalize it. Okay, generally, okay, this is the relationship. Okay, so let's look at this techno part. So the equation of regression line for independent variable x, we call it the predictor, and a dependent variable y, a predictant, is equal to what it becomes. This is actually, you see, y hat equal to mx plus b. So I think this, you are very familiar with this formula. Okay, in your, let's say, Form 4 maths class. Okay, y equal to mx plus c. You always hear this, y equal to mx plus c. Where y is the number in y-axis equal to the slope, m is the slope, x is the x-axis, of course, plus the interception. Yeah, obviously I already wrote there. Yeah, so m equal to slope of line, b is the intersection of the, at the y-axis. So this is known as linear regression. Okay, so this is actually very useful when we want to predict something. Okay, this is a very simple statistical model, the most fundamental of primitive statistical model that we want to predict something. Okay, let's say we want to predict y based on x. Okay, so based on the data that you have, you find the regression line. So when you find it, you get a formula. Let's say y equal to 2x plus 10. Okay, so when you have this formula, right? So now you want to try to predict y. So I just give you a number of x. So you just fit the x into the equation, you will get y. So you know y, where likely y will be. Okay, so this is how usually regression is being used. Okay, but next. Okay, so when you do regression, you have to always first visualize your data. Okay, so you can see from this Francis Anscombet, I don't know how to pronounce it, it's a French person. He demonstrates the importance of graphic, I would say, make your data a graph. Okay, plot the data out. Okay, plot the data out. Why? Because you can see he presented four cases. He have the same mean, same variance, same. Okay, so I mean the mean. Basically the same mean for x, mean variant for x, mean for y, variant for y, and the same correlation like this. Okay. I mean obviously it looks it's the same lah. But what I mean is you can have cases, 4 different cases with the same setting like this. Same mean of x, mean variant of x, mean of y, variance of y, and you have a very high correlation, right? And you do this and you calculate the regression line. You get one blue line like this. Okay, you did not plot your data, you just do like this, you get something like this. Oh, you say the regression line is like this. Okay, this is the regression we get from our data. But it can be misleading. Okay, so you have to plot out your data. You can see in the first case, yeah, this regression probably is okay. I mean, this regression is perfect. Okay, it fit the line, the data nicely. Okay, in this case below, maybe it's still okay, but you can see it deviated, the line deviated. The data deviated from the line. It's not the best fit line because it's impacted by this outlier. Okay, so rather than going going a bit vertical, right? It's supposed to be a bit vertical. Our line become more vertical, right? Going towards higher into this y-axis rather than actually fitting the point, right? You see this case. Yeah, the line should be like this. I should draw it. It should be like this, right? But because we have this very fixed value, so the blue line, it becomes higher, it go higher, right? So and another case like this one. Okay, this is totally not linear regression. The relationship is not linear, right? Like this. In another case, it's just one straight line like this, right? But because we have a value here, outliers, so it makes us, hey, we have this fitting. Yeah, so it can be very misleading. So if you calculate the regression without knowing the nature of your data, so if you want to do a regression, in fact, actually correlation, and regression, you should always plot your data out first, the first step. Okay, when you want to do correlation or regression, it is always important to plot your data out. Okay, this is called a scattered plot. Okay, you plot the X and Y data together and you see. Okay, then you only decide what are the relationship actually exists in your data. Okay, always remember this. Plot out your data first. And another is a multiple regression. It's a very useful thing. Yeah. So another for other form of regression, multiple linear regression. This allow us to compare the importance of X, the predictor. Okay. So let's say we have a different parameter. So we can, I mean, by calculating this multiple regression, we calculate this alpha. Is it called the regression coefficient? So it can tell us how important x1 or parameter 1 or variable 1 is to y. Okay, so it can tell us how important the different variable is to predict y. Okay, so this is the importance of, I mean, this is the usefulness of multiple regression. Okay, so of course you have to always remember the number of parameters should not exceed the sample size. Okay, so let's say your sample size have 30, so but you have the parameter have like 50. So I mean, of course, you cannot use multiple linear regression. So always remember this lah. Okay. And another is non-linear regression. Yeah, you see the flat line. This is linear regression on top. Okay, so bottom is the quadratic. Okay, quadratic regression. This curve like this. Okay, because obviously you can see the blue one is a data. Yeah, the data spread in like an arc shape, not a straight line shape. Okay, so when you see your data like this, it is non-linear. Okay, and when you want to draw this best fit line, you can usually use like quadratic or some other method, okay, to draw the best fit line. So always visualize your data. Okay, then you see what is actually the relationship. Then only you draw the line. Okay, so this is regression. So by right, I want to end the class here, but I just remember this morning, there's one thing very important: non-parametric tests. Okay, so the previous 5 different tests that we just discussed are known as parametric tests. Okay, parametric tests basically are tests that has assumption. The test that has assumption. If you still remember a few minutes ago, when we talk about the test, we say the sample size, the sample must be normally distributed, okay, or it has a sample size more than 30, right? It has this assumption. Okay, if you don't have this, I mean, if you don't meet this assumption, most likely you cannot use the test. Okay, but if you still want to test your sample, you can use something known as non-parametric tests. Okay, so there are many like Menkendel test, Weibull or something. So I'm going just to show you a very simple test called Monte Carlo randomization test. Okay, Monte Carlo basically is the casino name. Okay, they come up with this method. So what Monte Carlo is? Let's look at what Monte Carlo is. Okay, so let's say we have this sample. Yeah, P1, 2, 3, 4, 5 under Pn. Then we have Q, 1, 2, 3, 4, 5. So we want to calculate the relationship. So we get R. So we ask, how significant is this R? The correlation. Okay, if we calculate, we get a R, let's say 0.0. So let's say our R value 0.8. So we want to ask, how significant is this? So you will tend to use t-test, okay, the parametric test. But what if we want to use the non-parametric approach? Okay, so we just remove t-test, we throw t-test away. What we can do, we randomize our data and calculate again the R. Okay, so you can see, so at first we have P1 to N, P1, 2, 3, 4, 5 until N. Then we have Q, 1, 2, 3, 4, 5 until N. Okay, so let's do our Monte Carlo test. All right, so we'll start to do randomization. So we take our P, the sample of our P, we rearrange them. Okay, we rearrange them, or you can just sample them Yeah, sample them. We rearrange. We start with a simple one. So we rearrange them. Okay. Now you can see. Now our P1 already cannot find somewhere, right? It become P2. The first value become P2. The second value become Pn. That value become P8, P10, P9, P3, the last one. So do the same thing for Q. Okay, so you randomize the queue, you rearrange the queue, or you shuffle the queue. Okay, like shuffle your card. So you shuffle them, you shuffle the P, you shuffle the Q, you calculate the R. Okay, R1. So next, the second time, you will shuffle them again. Okay, now you shuffle your card again. Sorry, you shuffle the number again, like you shuffle the card again. You shuffle the card, and you shuffle the number for P. And then you shuffle the number for Q again. You calculate R. Now you get R2. Do it for the third time. Shuffle P, shuffle Q, calculate R. Okay, you repeat this step 1,000 times. Eventually, you will get 1,000 R value. Okay, you can follow. Remember, so you started up with the data you collected. You calculate the R. Next, we want to test the significance of R. We don't want to use t-test because we hate assumption. That's it. Then what we can do, we use multicolor approach. All right. So to do that, let's try to test how likely we get this R by chance. Yeah. So what we can do, we just shuffle our data. Okay. So when we shuffle our data, it means our data now is just randomly distributed, okay, randomly spread here and there. All right. So we rearrange, we shuffle our data. Okay. P, shuffle P lah, then you shuffle Q. Right. Now you get a new set of P, new set of Q. Okay, I usually call it a random set one, like that. Okay, so you calculate the R value. So you do it the second time, the third time, the 1,000th time. Okay, so the 1,000th time you get 1,000 R random. Okay, so when you have this 1,000 value, you can plot the distribution. Okay, you plot the distribution and you decide what is the critical value. Okay, let's say if you're a two-tail test, okay, meaning it's actually correlated, or you can say it is negatively correlated, positively correlated, like depending on your hypothesis, you get your critical value, the R critical value. You just plot it in the Z-score, the score format. Okay, you get the critical value. So if the R from your sample that you do not shuffle, meaning your original R, let's say if larger than this critical value, or it is lower than this critical value, so it means the relationship is significant. Okay, so I'm not sure you can visualize this or not. So meaning your R, the R that you get is not from the group of R that you randomly created, or you create with Chin-Chai you created. It's not. Okay, the R you get is really statistically significant. Okay, so then you will say, all right, P and Q, they are related with significant level, blah blah blah, like that, at significant level or something like that. Okay, so this is non-parametric test. By doing this, we remove the assumption. Okay, we are using basically we call it a brute force lah. Okay, we let our computer run. Okay, run, get us the distribution of R, and then we calculate then we decide, is it does our R fell in this rejection region or not? Okay, then we decide that we accept H0 or HA. Okay, so this multi-color test, it can be used for many different statistics, just to test the significance. Okay, so the important part is you create a randomized data, you calculate the statistic, you get the distribution, and you calculate how likely the statistical value you get from the original data fell into this rejection region. Okay, so this is multi-color test lah. So usually some software maybe have this test, or if not, usually you just write it manually, okay, in MATLAB or R. It's not difficult. Okay, Okay, another thing to note before we end this class is randomization can be done with two methods. Yeah. First is the permutation, then the second is bootstrapping. So permutation basically just reshuffling, reshuffle your data, or it is called array. I mean, you get your data. Okay, let's say you have a set of data, you get it without replacement. Okay, so let's say if you have alphabet A to Z, yeah, so now you want to randomize A to Z, right? So you take the A to Z alphabet, 26 alphabet, you put in a box. Okay, you put in a box. So you randomly close your eye, you draw. Okay, first you draw maybe W. Second you draw Z. Then you draw A. So just write W, Z, A. So the one you draw, you no longer put back the box. So meaning, eventually you will not draw the same number twice or more than twice. All right. So eventually you get your randomized data set. It's called permutation, arrangement. Okay. So another method is bootstrapping. So bootstrapping is you draw the number, you draw the value, you put it back. Okay. Yeah, I mean you want to actually most method is easy. So okay, you just take the you just take the number. Okay, you say A to Z. You close your eye. You take is now let's say P. Okay, get a P. So you take the P. You write it down. P. You put it back the box. Then you close your eye again. You draw. Maybe you draw P again. So you write down P. Okay, so this method is known as bootstrapping. Okay, why it has two methods? All right, bootstrapping is very useful when your sample size is very small. Okay, when your sample size is small, you tend to want to use bootstrapping to do the randomization. If your sample size is large, you can use permutation. Okay, so people ask me, is it more difficult to do permutation or more difficult to bootstrapping? Basically, they are just the same. Okay, it's just the way how you code, basically. Okay, how you code. All right. I think that's all from me. Yeah, I know it's a very long class and tedious class. If you have any question, I welcome you ask me lah. Let me stop the recording.